Okay, so I'm Nick. I'm part of the Exotrix group at Berkeley Lab. And this talk is going to go over some of the learn representations that we use for the TrackML clustering. And this is a little bit of a continuation of Daniel's talk, going into a little bit more detail on a couple of the stages of the pipeline. And also it's going to talk about how we can use these learn representations for clustering directly. So just to give just a refresher on the TrackML data set, so we have about 100,000 hits on the detector created by about 10,000 particle tracks. And the idea is that given these hits, where each hit has an XYZ location and some information about how the hit what pattern it left on the cell. Given that we want to cluster the hits into K clusters, we don't know how many clusters there are, how many tracks there are beforehand, and we don't know how many hits should belong to a track. And obviously, we need everything to be efficient, because 100,000 hits, that can be quite expensive if we're not subquadratic. So a couple of the just to give a little bit of motivation on what helped me to look at this method. A lot of the top solutions to this TrackML competition, the first thing that they do is they identify pairs of hits where those two pairs are likely to belong to the same track. Using those pairs of hits, using that scoring metric, you want to construct a set of tracks based on these pairs, and then apply some sort of refinement. So you might reject tracks that don't fit a certain criteria, and then with any leftover hits, you might extend tracks that where the hit looks like it might belong to that track. Another baseline that we look at is my colleague Steve Farrell, his early work in GNN-based tracking. So here you have, you ultimately want to use a graph neural network to do edge classification. And the hope is to end up with a set of edges that only connect hits that belong to the same tracks. And in particular, they look at hit pairs on adjacent layers. So in order to use a graph neural network, you need to have a graph. And in this case, you want it to be as sparse as possible. And then once you have those edges, you can just traverse through the graph to form tracks. And if your edges are perfect, then you'll get a perfect 1.0 TrackML score. So in both of these cases, you have to go through a process of doublet building. You want as many true pairs of hits as possible, obviously, and as few false pairs, where a true pair is a pair of hits that belong to the same track, and a false pair is obviously between a pair of hits that don't belong to the same track. And so the key idea, one of the key ideas of this work is that instead of using a set of heuristics, like if these two hits motivated by physics look like they might belong together, why not just use machine learning to learn a representation of the hits, embed them into a new space, and in particular we use a Euclidean space, and that new space should have a Euclidean metric. So pairs or hits that belong to the same track should be close together. Hits that belong to different tracks are far apart. So to do this, we construct a data set. That data set consists of pairs of hits and their labels. And the pairs of hits label as 1 if they belong to the same track, otherwise 0. And the embedding model takes in one hit, which has the XYZ position of the original space, as well as the cell direction information, and embeds it into this new Euclidean space, which has an embedding dimension of M. And in our work, we use an embedding dimension of 8. Then what we can do is we can supervise these pairs of hits. We can take in a pair of hits and supervise their loss by this hinge embedding loss. And basically what it's trying to do is that if the pair of hits belongs to the same track, then we just penalize whatever the distance is in the embedded space. If they don't belong to the same track, then if they're far apart from each other, we don't care. But if they ever become close together, then we apply a penalty. So in pictures, on this left plot, we start off with a seed hit. This center plot shows the embedded space of all the hits. The seed is shown in black here, and then its neighborhood is in red. And then projecting back into the original space, this seed hit belongs to this track as shown in yellow. And these are all the hits that are within that neighborhood. So from a very large set of hits, we're able to recover all of the hits that belong to the same track as the seed. And we only have a very small set of false hits. Okay, but we can actually do a little bit better. So unfortunately, graph neural networks are very memory intensive, and that scales linearly with the size of the graph. So the more sparse that we can make it, the better. And the other aspect is that there's a lot more information content in a pair of hits than there is in a single hit. So we can actually do a refinement stage where, given a seed hit and its neighborhood, we can compare that seed hit to all the hits in the neighborhood and actually perform a classification task. So this is a very similar data set as what we had before. The difference is that now we're going to have a multi-layer perceptron which takes in a pair of hits and classifies whether or not they belong together. And so doing this, we can filter out a lot of the false pairs to get a much more pure graph. So what this looks like is that on the left, we have a seed hit and its neighborhood. We pass the seed hit concatenated with each one of these neighborhood hits individually. And so after this filtering stage, we have a much more pure neighborhood based off of that seed. And in particular, we improve this the purity of our graphs by about 17%. So we greatly reduce the number of edges going into the GNN stage. So the full pipeline will look like, starting on the top left here, we start off with a seed shown in yellow, and that seed's track hits. On the right, we have, this is for a full event, so there are actually quite a few neighbors seeded by the embedding neighborhood. On the bottom left, we're left with a neighborhood which is much, much smaller after filtering out most of the hits using the MLP classifier. And on the bottom right is what it would look like if we just directly went to a GNN. Okay, so to give some numbers, the learned representation pipeline finds about twice as many true doublets, so the efficiency is about twice as high as a physics-inspired cut-based approach. Because these, in the embedding and the filtering stage are parameterized, we can actually change how efficient and how pure we want them to be. So we can have adaptive neighborhood size in our GNN graph. The nice thing about this approach is it's plug and play with the baseline, so we can basically swap out one of these physics-inspired graphs for our learned approach, and we have a much more pure graph, which runs a lot faster because of how much smaller it is. Talking a little bit about speed, so the results shown on the previous page are with full precision, using an MLP for each stage of about 3 layers and 512 hidden units in each layer. we can actually do quite a bit better than this going to half precision. We can get almost a perfect 2x speed up so that the graph building procedure on the whole takes about 1.5 seconds. And the difficulty here is we're still having some trouble with convergence, but the nice thing is that going to half precision really doesn't change the results too much. And so we're still exploring how can we further reduce the network size. There are a whole bunch of different optimization strategies for getting that speed down even more so that the embedding stage takes below 1 second per event. Okay, so I'm going to transition now to talking about track building. So in Daniel's talk, the idea, a lot of what he was doing was taking in the graphs built by this learner representation and then producing a set of triplets. And his triplet classifier is extremely efficient and the purity is almost perfect. So the question is, given a set of triplets, how can you stitch them together to form tracks? Now, we can do basically the same approach with triplets as opposed to doublets, where we learn an embedded space of the triplets, the embedded space as a Euclidean metric, and then we sample in the embedded space to find triplets which are close together. So the data set is almost identical in this case, except that now we have pairs of triplets, and because the output of Daniel's triplet building stage is so pure, we can assume that the triplets, each of the 3 hits in each triplet, they all belong to the same track. We supervise this with a hinge embedding loss, and let's see, so, and then the full pipeline would be that we first receive the triplets with high purity, and we then embed the triplets using our learned embedding model on triplets. We query the neighborhoods, filtering pairs of triplets, and finally, we can build the tracks iteratively. So we look at a triplet, we look at its neighborhood, and we assign all the hits inside of its neighborhood to the same track. So what does that look like in pictures? On the top left, we start off with a triplet seed and its tracks. On the top right, we find its neighbors in the embedded space. On the bottom left, we have just those triplets projected back into the original space. And then on the bottom right, we filter pairs of triplets using our filtering model to produce a final track. I'm going to skip the second example in the sake of time. And so Daniel has done a little bit of work since I've gotten these results, but looking at the full event from his triplet producing stage, the best track ML score you could get in this case is about 0.82. I know he gave a little bit higher numbers, but he has since improved his pipeline. And so this learned track building using triplets, the best we can do with track ML is about 0.78. Now that isn't extremely good. However, given that the best we could possibly do is 0.82, we're actually able to recover. We're actually able to recover quite a bit. So just very briefly, after we have looked at triplets, we can actually extend this out to tracklets doing something very similar. Instead of looking at a triplet and embedding it into this Euclidean metric or a doublet where we take a single hit, we can actually take a track segment and embed it into some new space. And so here the major difference is that as opposed to looking at our data set consisting of pairs of hits or pairs of triplets, now we can look at it as pairs of clusters. The major difference here is because we have variable sized clusters, we'll have to use a GNN model to take in a cluster and embed it into a fixed dimensional space. But doing this, we can actually build up tracklets or tracks directly and not have to go through this hit or triplet metric learning stage at all. And this pipeline would fit right into like an agglomerative clustering approach, where you could first go from pairs of hits into and bring them together to form clusters, and then from those clusters you can iteratively cluster them together until you form your final tracks. So in conclusion, some future directions: we want to we can actually do a little bit better with the track ML score by improving the metric learning stage and in both the doublets and the triplets. After we have come up with our triplets forming into tracks, we actually have quite a few leftover hits. So incorporating those leftover hits into the tracks would recover some of the track ML score. We can improve each one of these stages by incorporating perhaps a better loss function, or use a different embedding space, which is more natural to the physics. And finally, we can improve the graph building phase to balance speed with efficiency by considering different neighborhood sizes or filtering thresholds, and continuing to explore different avenues for improving the GPU speed of the multi-layer perceptron models. That's everything I have. Thank you.
Great, thank you very much. Interesting. As usual, I'm looking for raised hands. We have time maybe for one question. I don't see anything. So I will ask one then. If you go back to your slide 6, I think, where you have the picture, yeah. So if I understood correctly, the learn and embedding basically takes the map on the left and then puts it in. Of course, it's multidimensional. This is just showing 2 dimensions, but puts it into a new map, which is basically some transformed coordinates, so that now each hit the hits in the same track are close together. And you only do that once. You don't have to do it over and over for each hit, but you have to do it over and over.
Yeah, exactly. So because the multi-layer perceptron acts on each hit individually, that embedding only has to happen once, and then you can query really efficiently in this embedded space using something like a KD tree.
Yeah. Okay. So all the hits get processed together, basically into this space. But then where a given hit ends up on that space depends on the other hits. It's not like you can just, if you just give me a hit, I can put it in the new space without knowing anything else, right?
So actually, in this case, we're just looking at one hit. So based off the XYZ position and the hit, the features that are left on the cell, we have enough information to already get a really good neighborhood just by embedding each hit individually.
I see. So each hit doesn't have to know, it doesn't matter where the hits are. Each hit will always end up in the same place. A given hit will always end up in the same place in the transform. Yep. Okay, very good. So it's kind of in spirit similar to a half transform, except for the transform space is also you go from a point to a point, not from a point to a line or a shape. Good. Any questions? I don't see any other questions, so I think we'll thank you again and we move on.